Okay, guys, let's just stop. So we stop here. The previous session that was about manometering and talk about how we can solve the questions of piezometer and YouTube manometer and bunch of the advantages and disadvantages of simple type of manometer, and then talking about advantages of YouTube manometer. If you remember, we talked about how we can, that's my method. I don't know the others, how they're using, but I will tell you maybe the other solution if you see how they're going to, what's the approach for solving the question of manometer, but that works for me. So if you are not happy with that, you feel free to use any method that works for you. So that was the method that just pick a point, then try to escape. And if you're moving in a horizontal line, then nothing gonna change. So these are going to be the same points, but when you are going up or upward, you have to use negative sign, and you are going downward, you have to use positive sign. Okay. Okay. Then, and when you are escape, minus the P of n equal to 0. One point is that we don't care about the reference. For example, the reference was z equal to 0 is here, then this one is going to be minus h1 over 2 and plus h1 over 2. You're talking only about the distance between these two. So because you are using the positive negative sign here before that, then you don't care about the distance or the numbers versus the uh, reference point. We're talking about the distance. Then we talk about the advantages of YouTube manometer, that how we can calculate the pressure of a gas container, and it's helpful to find the pressure of this container even if it's lower than the atmospheric pressure. Then use our method here to check that it's going to work or not. So if you see the solutions, it moved from point A to this line, right? Then measure, okay, so we don't, the Z or depth doesn't change. So these are the same line. We can easily come here. So still PA. Then coming down to this line, right? Coming down to this line, why? Because here the fluid is going to change. This one is the gas and this one is the liquid. Coming here, stop here and writing minus gamma or plus gamma 1 h because you are coming down, right? But from here, they are not coming down here and here. They're jumping from here to this point 3. That's why we have point 1, 2, and 3. They're jumping to point 3 because they're at the same line, right? But why I don't like this method? Because if you have a liquid here that the interface is lower than that, that you cannot use it. You cannot jumping from here to here. Why? Because you don't know the pressure difference here. As long as that you are in the same fluid, you can move horizontally. But if you have two fluids, for example, you cannot move from this point to here. Why? Because these two absolutely have the same depth or height, but on top of this point, you have gas, on top of this point, you have liquid. So that's why it's not, or you have to be careful when you're using that. For me, that's gonna work. And I guess I have to try it for more examples to show how you can use it. So here we use this method and solve it. The third advantage of the YouTube manometer is different between two gases. So you have two containers, A and B. Now you're going to find what is the pressure difference between these two. Okay, so let's try. First, pick a point, which is A, right? Then instead of try escape, you can move this line, move through the tube, and going to P at the B point or PB, right? So first, you have PA. A little turn it and write it. Okay, you have PA. Somehow you have to see it. Okay. Then you're moving in this line, so nothing changed. That's H1. Also, guys, I put all the notes after filling the shell in UV lens, so you can download if you cannot see it clearly, because I cannot at the same time zoom in on the numbers and the points and parameters here at the same time writing. So you can follow it from the notes PDF files. Okay, so if you are moving here in the point 1, nothing changed. But when you're going down, then you need to use plus gamma of that fluid, gamma 1, then H1, right? From here, you are coming down. What's that? Is H star. You stop here because the fluid changed. Now you are moving down because of H star. Gamma is gamma 2, the second fluid, and H star, but use positive sign. Then moving on the line, nothing changed. Going up, the same H star, but negative sign. All right. Then moving more, again, this line, which is H2, or you can move from here to here and write that minus gamma H star plus H1, nothing changed. Sorry, H2. H star plus H2. You are here, then fluid change. You have to stop here and change the gamma. Negative gamma 3, H3. You are here, over the line, reach PB, then minus PB equal to 0. Okay, gamma H star is cancelled out with this gamma H star, and just going to keep it. So delta P here equal to, bring this the other side, gamma 3, gamma 2 first, H2 plus gamma 3, H2 minus gamma 1, H1. Okay, that's it. You have the answer. But that's a hint for you guys. If you have gas, like the containers are fluid, right? If the container is gas, then the gamma of gas is not that much huge, right? So most of the time, they will consider that this gamma 1H, gamma 1H1 here, the difference between these 2 points are negligible. And also from these 2 points are negligible. Then you can write that, okay, if assumed by the question that the gamma of the gas is negligible, then you can bring PV here and then come here without changing anything. Why? Because these are gases and you are going to calculate the pressure of gases. And the pressure differences is only gamma 2H2 because gamma 3H3 here and gamma 1H1 are negligible. So it's possible that the question tell you that because of these are gas and you can ignore it, then remember to how does it mean? Okay, any question till now?
What are the units on gamma?
Gamma or rho G? Gamma unit, gamma is rho G, right? The unit of rho is kilogram per meter cube times meter per second square. One meter here going to cancel out. And if you multiply that by distance is meter going to cancel out with another one, then kilogram per meter second square is possible. Newton per meter square going to be extracted from. Clear? I was never thinking about the unit of power because the only thing that I care about is rho and G. And delta P, as we mentioned before, is rho G H or delta H. Then rho G just replaced by count. Okay, let's talk about inclined tube manometer. So when you have inclined tube manometer, what's the point? The point of using the inclined tube manometer is it's a space that the main advantage is that the small pressure changes between point A and B going to be detected by the manometer. So why? Because the detection of a manometer, it depends to the height differences, right? It's possible that you're doing watching the two manometers and you want to measure the difference of pressure based on the height change between these 2 points, right? But when the pressure of these two are very similar, then absolutely the line or the height of the tube are going to be the same, right? It has to stop in one point or very similar. Then you cannot find what is the difference between the heights to find the pressure difference. At that point, the incline is going to help you. Why? Because if you see, the only thing that we care about is the depth of fluid, right? Even if you have a difference in like inclined, moving the flow like L2 here, right? Still, the pressure difference, it depends to the theta and how much the fluid moves upward. That's going to be H2, right? From here is our H2, which is 2 sine of that. Okay, so if let's consider that the delta P or the pressure difference is very small, or a constant number. Then if H2 is 1 millimeter and you decrease the theta from 90 degree to that is here to 10 degree, then absolutely L2 or moving the fluid in the tube would be H2 over sine of theta, right? When you decrease the theta, the sine of theta are going to decrease. These are linear. Then H2 over sine of theta, because sine of theta decrease, H2 is constant because the delta P is constant. Then L2 would be increases because the sine of theta is in denominator. So L2 increases means that with the constant pressure difference, you will see huge difference in moving the fluids. That's why you can measure it with inclined tube manometer. I wrote it here, what is H2? And I will going to show you that if that's the point, this line is also H star. Okay. And what else I need? That's it. Let's start with our method. Start with point A, PA. Then from here, nothing changed. Then you're coming down. Then you're coming down. So it means you have to use positive sign. Gamma 1, H1, because this is H1. Then this line from here to here, you're moving. You're moving in the second fluid. That's a blue one. How much you are coming down is H star, because this line from here to here, I put the name of H star. Okay. So you're moving down, then plus gamma 2 H star. Perfect. But from here, when your point is here until this point, how much you are moving upward in positive Z is like this. But how much you are moving upward is again H star. Upward is negative, gamma 2 H star. You're coming in this point, right? Then I'll write it here. From this point to this point, the H2 is the depth change. So minus gamma 2 H2. You are here, then you're going to come there. Why? Because that's PB, and the rest of it is going to be horizontal movement. So this is also PB, right? From here to here, you're moving upward, minus gamma is gamma 3, and the difference is H3. Reach the minus PB, minus PB equal to 0.
For the grading in this class, are we going to be required to write out the canceled terms?
What?
For the grading in this class, are we required to write out the terms that end up being canceled?
No, no, no.
Okay, thank you.
No, no. But if you mean that not writing the terms that we're going to cancel out, then means that you're using the other methods, like even the solution of the homeworks or the solution of the books, that are jumping from this point to this point, right? They're not writing these two changes that are going to be canceled out. Why I'm telling you this method? Because at first it's unclear for a bunch of the students that how we are jumping, right? When you're doing this method for 1, 2, 3 or more times, then when you see the example or any question, you will know that, hey, I'm going down, then going up here. So why writing that? Let's cancel out right now. Then it helps you to faster jump and understand why you're doing this jumping, right? That's why I'm writing that in the basic one, try to escape or passing through all the tube line. When you are happy or understand that while you are doing the jumping, absolutely that's much better. That's much faster, that's much better. And you don't need to, if you do that, no one going to cancel, deduct any points from. Okay.
All right, I have one more question. Is there ever a time where you go horizontally and you're changing liquid fluids in a horizontal plane, like in the X plane?
Never changing any.
Like if you know the and fluid that's in the one of the enclosed, it goes down and it stops in the like. I'm looking at the YouTube thinking of it in that one. If in the part that's flat at the bottom, if you broke in the middle and you had one type of fluid on one side and the other type on the other, does that ever happen or no?
This is not gonna happen. You know why? So you're talking about let's say you have here, okay? Then you mean that you have 2 points moving horizontal, right? That was the question.
Yeah, and then like
In
say in the
reality,
middle of it, you have it. Can you change fluids in the middle of that? Does that ever happen?
what does it mean? The fluid change in the middle of that?
Like say, I don't know, a gas on the left and whatever liquid is in the manometer on the
Oh,
right.
you mean that there is interface of the fluids here?
Yeah. Does that ever happen?
I'm thinking about how
I
physically
don't
it's
think it
possible.
would, because I think like they would mix, right? If that was
Could be.
to be the case.
Oh, no, it's possible that you have two fluids that not gonna mix, but it's not possible. Absolutely, they're going to mix. They can be on top of each other, right? For example, fluid and gas, fluid and
Yeah,
oil,
if one's denser than the other, yes.
but not in this way. But let's say in imaginary world you have, okay? Then absolutely the fluid in these two, the pressure in these 2 points are different. Why? Even in this point, you see here,
Yeah.
from this line to this line, from PA till here, nothing changed.
Yep.
But suddenly when you move from the interface, the pressure change. Why? Because for each of these points, you have line of the P atmosphere. So pressure at this point is P atmosphere plus how much of the volume of or weight of fluid on top of this point is. That's the pressure at the point, right? So how much we have here, the same. But when you're changing the fluid in horizontal way, then you have P atmosphere here, but the weight of fluids is different, right?
Yeah, I get that.
For
I
whole
was just
this
asking
point.
if it ever happened.
Yeah,
Like I can't think of.
if it happens, then yes,
Okay.
absolutely you
All right.
cannot move horizontally. But I don't know that there is any example like this.
Yeah, I can't think of an exact one either that it would. But I was just
Okay,
curious.
yeah, and we cancel out these two right now, and let's say the pressure difference PA minus PB, right, is gamma 2H2 plus gamma PH3 gamma 2 gamma 3 minus gamma 1 H1. Okay. So I wrote it again in the notes that uploaded right now. So if these are gases, then gamma 2, gamma 1 and gamma 3, not this one. Gamma 1 and gamma 2, 1 and gamma 3 could be equal to 0, right? Then you can cancel out these two, not cancel out 0. then the delta P is going to be only the pressure difference, right? As you see here, that's why this inclined tube manometer designed in a way to have the second fluid, which is, or most of the time, liquid, because it has higher uh, gamma, is at the middle or in inclined part, right? Because if you use the gases, then you don't care how much the gas is here or here, but you care only about the fluid, because this is responsible for finding the pressure difference in the containers. Finally, delta P is equal to gamma 2H2 or gamma 2L2 sine of theta. Again, sine of theta. Yeah, because of the homework, I'm going to explain this one as well. So let's say you have the fluid at container A, just replicate 2 times. Or A and A. Everything are the same. Then these are, again, imagining. Let's say you have container A, but you have only one at the time. Then you will have another line here, which is container B. Or you have inclined version of that. And this is stopping here. That's container B. So if the difference between these two containers is very small, right? If that's very small, then this H, you have to know that, can you read from the measurement the item or something like manometer, that can you read the H difference or not? If you couldn't, you can use the inclined version, that the same pressure difference is higher in the inclined version, and we can read. That's why the inclined tube manometer used for high sensitivity as a high sensitive measurement tube, manometer. I don't have it, but I guess you have one more with the additional topic. I wrote another example for you guys with my manometer, but if I get time, I will solve that again for you. But much more important right now is talking about the buoyancy, because this is going to take time and you need it for your next homework. Buoyancy. Do you think that the quality of the video is not good? Jackie? Have to clean it. Yes. Okay. Buoyancy. It's basically based on the Archimedes principle. Let's say Eureka. You can see it. That what was the finding of this the Archimedes, that a resultant force acting on an object that is either completely or partially submerged in a fluid is called buoyant force, or FB. Okay. For example, this one is partially submerged, and this one is fully submerged. Okay. What is a buoyant force? Is a net upward vertical force results because pressure increase with depth, right? Pressure difference in depth. The pressure forces on top. So if you have a shape or arbitrary shape, you have force on up because of the pressure, and you have a pressure at down that give you force at down, right? So, and this is liquid, and this edge is not negligible, right? Then the forces are going to be different. Absolutely, the P of the pressure of up or lower than pressure of down, right? So the force at top is lower than the force at down, right? That's why the buoyant force to the object is upward. Again, buoyant force is based on the force that the fluid act or exert on uh, the object. So let's consider that you have an object here fully submerged. Then also think that this is a 3D shape. Okay, so you have this shape again here. Hmm, so it's a 3D one, right? I put the A prime here, B prime here. And this is going to be C and D, C prime and D prime. So that's a 3D, right? And also, if you see here, if that's the object, the rest of this box is going to be filled with the fluid, okay? Now, in this uh, control volume, that's the line, or this line are showing your control volume. So the force F1 is actually act on the center of the surface, right? So F1 actually act on A prime, B prime, B, this surface on top. And also F2 is on CD, C prime, D prime, D. This is the x direction, A, and buoyancy. It's obvious here. And the point that passing the F1 is going to pass through is the center of the surface, right? So absolutely, this is going to be passes through center of the surface, which is rectangular shape at the middle of that. But that obviously is a question for you guys, that why buoyancy is downward here, right? Absolutely, you have that question. That if we mentioned that the buoyant force is upward, and it also mentioned here that the buoyant force is upward, why we have the W, which is the weight of the weight, that's it. We'll talk about that. What's the weight of this object? Is object or the fluid? And also we have the FP here that is downward. So because we are not writing the equation and force balance for the object, we are writing the force balance for the fluid. So for example, if you bring your hand and keep a glass on your hand, then you have two forces. If you write the force balance for your hand, for the glass, then hand that keeps the glass is going to act a force upward, and energy of the glass is downward. But if you write it, that force balance for your hand, absolutely one force is the weight of your hand, but the object, which is the glass, act a force on your hand, which is the pressure. It's like a pressure, and it's because of the weight of the glass, right? Here is also the same. We have fluid here, and we have the object there. But the object acts a force on the fluid part because it has a weight, right? Because it's easier for us to write the force balance for the fluid. We are saying that, okay, everything is based on the fluid. We have a control volume. We don't care that how much of this is filled. We put the boundary of the control volume outside of the object. So everything in, if there is object, is inside of the control volume. Then let's write the boundaries and the forces. So one is the weight, which is the weight of fluid. We are talking about the fluid. We have FP because it makes easier. This FP is for body, right? That's why we have P. But this is for the force that is act on the fluid because of the weight of object. This W is not the weight of object. If it was, it should pass through the center of the mass of object, but it's not. It's only the weight of the fluids that we have in this control volume. Then the forces at the boundaries. One is pressure at top, bottom, and this right and left, right? Okay. But before going to see the force balance for this part, I will tell you that if you have any buoyant force, the buoyant force going to pass through passes through the centroid of volume. Centroid of volume, or center of I, it may also known as center of buoyancy. Center of buoyancy. That, for example, is C or CG, right? But if you have this object and you find the center of buoyancy, and which is the center of volume of that, doesn't matter that this maybe you have a volume like this arbitrary, and this is the center of the volume. but it's not a homogeneous material inside of that. Means that here maybe you have a higher weight of, this is not homogeneous, it's heterogeneous, or you have a higher weight of the material here. Then the center of volume and center of the gravity are not matched together, right? It could possible that center of gravity is here. The weight or mg passes through it. So these two are different. The weight or the force that you have to write it in your force by diagram depends that where is your center of gravity for W and where is your center of buoyancy for FB. We'll talk about that how the point going to affect the stability of the object, right? But right now, you know that what's the difference between these two and why we are talking about it. Okay, let's write the force balance here for the same shape and we'll bring it here. So let's write about let's talk about the balance forces. These are balance forces for fluid. Okay, we didn't show here, but you will have also an X direction, right? So you have a surface like here, you have a surface at and force here and another force here. But it's obvious that these are not going to change because this, if you have a center of the surface, that because this is rectangular shape, the center of surface here and here are the same, right? When the points are in the same line, it means that the same depths of fluid are on top of it, right? Then the force at first, the pressures are the same, the area are the same, so the force is going to be canceled out each other. So these two forces are going to cancel out each other. Then why that we wrote it here that Fx, because it's not shown, is 0, but Fy is also is 0 because this one is not shown, but is 0. The only thing that matters is C. Have the same depth. Okay. Again, this FB here is the body. Better to mention here. This is the force that object exerts on the fluid. And you know, when you find that up the force, because of the Newton's third law, the force that the object acts on the fluid is equal, but in this other direction of the force that fluid acts on the object, right? So the force that fluid exert on the object is the buoyant force, right? These two have to have the same magnitude. This F body is the one that you calculate here. If you find the F body here, the buoyant force is also the same in magnitude, but in the different direction, right? The F body here is downward, so the buoyant force is upward. That's why if you find the FP, you absolutely have the buoyant force. So in Z direction, you have one force at top, F2 at bottom, you have W of fluid, weight of the fluid, and you have the force that object acts on the fluid, right? So F2 is the only one is upward, okay? F1, W fluid, and W FP are downward, right? Also, I'm writing body here again to make sure that this is the body one. If you write the FP, that we are writing this force balance to find absolutely FP, because FP is going to be F body and F body is going to give you the buoyant force. So FP is equal to F2 minus F1 minus W fluid. So what we are going, that's I wrote the name of one here. That's the first equation. And in this equation, you have a problem to find F2 minus F1, right? So F2 minus F1 is P2 minus P1 times area, right? Because these are the forces created because of the pressure, right? Okay, so F2 is P2 times AS, and F1 is P1 times AS, right? AS also is the area of the surface, right? The area of that multiplied by the pressure. It's actually surface of A prime, B prime, B. Okay, so till now you know what is the AS and the pressure brought in here. But what about the, if you want to make it easier to see what is the pressure difference here, is equal to gamma times difference in H. H1, H2, right? What the force here, the pressure here is gamma, the pressure here versus the absolute gauge pressure here is gamma H1. The pressure here is gamma H2, right? Delta P between these two surfaces that gives you the net force is P2 minus P1 equal to gamma times H2 minus H1. If I write that this is H, capital character of the H, then I can write it here that gamma times H2 minus H1, this is H. Okay, perfect. We have P2 minus P1, and if multiplied by AS, we can find the forces. Let's talk about the volume. That's the second one, right? That's the second equation. But this is the third one. What is the W of the fluid? The W of fluid, again, if you check the 3D, you have a box. What is the area of the box? Is H times this side times this side, right? That's the whole volume of the box. But how much of that is filled with the fluid? Absolutely. What is, at first you have to ask, what is the volume of the object? If you deduct volume of the object from the whole box, then the rest of that is going to be fluid. What is the area of the blue surface? The area of the white surface minus the area of the rectangle. The same for the volume. That's why we wrote it here. The W of fluid is actually the gamma H2 minus H1 times AS. This is the volume of the box, right? I can write that this is the same as capital H, and the whole is volume of the box, correct? That's the volume. And what about this W? That, I'm sorry, what is about this volume? This is volume of object, right? The gamma is the gamma fluid, right? Gamma of the fluid. Just for, because I know that maybe that's a question. We are not getting the volume, we are not calculating the weight of object to deduct from the weight of the fluids. we are getting the weight of fluid using the volume. Then this gamma and this gamma are the same for fluid. Yeah, absolutely. You have two methods to find the weight. One is gamma times the volume of the object. One method is finding the rho times the volume. Here, because we are using gamma, we don't have gamma for a solid object, right? That's not gamma. That's going to be rho times the volume. Since we are using gamma, this is gamma of fluid, and this volume of the box minus volume of the object gives you the volume that is filled with the fluid, right? That should be cleared. So what's next? Using 1, 2, and 3. How we are going to use? First, replace P2 minus P1 equation inside of this equation 2, then replace F2 minus F1 on equation 1. And also replace equation 3 in equation 1. Why? We have W of fluid and we find W of fluid here. Okay? What will happen? It will happen that if you lose the magnitude, F of body from equation 1 that we know is downward is equal to magnitude of F of buoyancy, which is upward, right? Equal to first F2 minus F1, which is gamma H, because of P2 minus P1 times AS, okay? That's F2 minus F1, minus gamma of H AS step, and minus because the minus sign here before W of fluid, plus gamma in volume of the object. These two are going to cancel out. That's the final equation for finding the volume, the buoyant force. If P equal to gamma of fluid times volume of the object. Again, that's very interesting. That's why Mr. Archimedes was so happy when finding it. When you are going to calculate the force that the fluid acts on an object, you will use the volume of the object, but multiply that by the gamma of fluid. What does it mean? Literally. It means that buoyant force has a magnitude equal to the weight of fluid displaced by the object. When you bring the object into the, or partially or fully, into a fluid, it comes in, but at the same volume of that, fluid moves upward, right? Or displaced. That's why the same weight, the same weight of that displaced fluid is the force that fluid act on the object upward. Very interesting, at least for me. Now displaced volume, displaced fluid is the volume of the fluid times the fluid specific weight, right? That's the gamma fluid. But we know that the volume of the fluid that displaced is equal to the volume of the object. An object with the volume of 1 cannot displace volume of the fluid more than its volume, right? Or lower than its volume. When volume of the object is equal to 2 meter cubed, absolutely the displaced fluid volume is 2 meter cubed. That's why we replace these two, and we find that, okay, when you have an object, find the volume of that, multiply by the gamma of that fluid, then you have the buoyant force. Here we are talking about the stability. At first, meaning of stability means that the stable one is in a state 1. If you move it to state 2 and it return back to the same state, the same condition, then we say that, okay, that system is stable. But if you change a state 1 to a state 2 and it's not coming back to the same situation, then the system is not stable or unstable. For example, that's the meaning of, that's why I told you the CG and C, or buoyant, center of buoyancy, are different, and it matters. Why matters? Because of the stability. For example, you have an object here with state 1, and you see you have more weight, more of the material here. It shows down there at first because you know what is the direction of the object, and also because you see that it's not homogeneous material. Then you have more weight here, more material here, more mass here, and center of the gravity coming down and move to the high mass part. The CG is here, and center of the buoyancy absolutely is the center of the volume, right? Is at the center because the shape is symmetric. Okay, you change it to state 1, from a state 1 to a state 2. Then when you change to a state 2, you see that it gives you a rotation force because the distance between the horizontal distance between C and CG, and because the forces are give you a counterclockwise rotation, right? And you're restoring to the same state, state 1, then you say that, okay, this system is stable. But if you have the same state, but the force at top, CG at top, and buoyant force at down, right? And you change it, you apply the same change or increment of rotation and make it state 2. Then these 2 points give a clockwise rotation. It's going to return or going to turn and turn to reach another stable state. If you compare the state that you finally have with the state 1 that you had before, if these two are not the same, the system is unstable. That's in the chemical systems as well, or in thermodynamics. When you are going to check the differences in a state of any control volume or any shape or any box of fluid, you apply the heat, apply the pressure, or anything that make changes on that object or volume. Then wait to reach another stable station. When you reach the stability again, then compare your situation, first and the second. So here we also did that. The state 1 and state 2, we compared these two and found that, okay, this is not the same. So the system is unstable because it's not returning back to the same stability station. Okay, that's the buoyant force. Let's solve an example. A sealed rectangular shaped container filled halfway with gas is partially submerged in water, right? The specific weight of gasoline is 6.5 kilonewton per meter cube, and if the width of the container is 1.5 meter, determine the weight of the empty container. The weight of this part, because this part also have container and is filled with gasoline, right? First, this is empty. And the width of A means that in Z, if that's Y is X, and that's the Z, in Z direction, W is 1.5. Okay. Force body diagram. Gasoline, and this is Y direction, right? Let's see that that's the W. That's our equivalence. Again, these two should be in the same line. Why? Because the state of this box should be stable, right? You're waiting that this is stable, then you're starting your calculation or force body diagram. So these are the same line. What is the volume of container? To write the sigma of y here, at first, let's write that WT, first buoyant forces upward, the F of B minus WT is equal to 0. Right? So FB is equal to WT. Thus, base comes from the force body with the force balance. V of container is 1 times 3, 1 times 3 times the W, which is 1.5. 1.5 is give you 2.25 meter cube. Okay, that's 4.5. 4.5 meter cube. What about the V of the gasoline? For the V of gasoline, you know that half of the container is filled, right? So the V of gasoline is V of container over 2, which is 2.25 meter cube. V of gasoline and V of container. And also, you know from this also shape that the volume of empty space is also equal to V or volume of the gasoline. So here also you can write that V of empty is equal to V of the gasoline, and equal to V of the container over 2. Okay, we find that WT is equal to FB, right? What is the WT? WT has to be the W or weight of empty part. Just write it with E. The empty part plus the W of gasoline. Okay. And the question is that how much is the weight of the empty part? What is the weight of gasoline? It has to be the volume of the gasoline times the gamma of the gasoline. What about the buoyant force? What is the buoyant force? It's the volume of this place, or we mentioned before that this is volume of the object that is inside of the fluid, right? Volume of the object times the gamma of the fluid, right? The fluid here is water. Mentioned here, that's what. The gamma of fluid times the volume of the object, okay? Volume of the object, volume of the displaced, and volume of the gasoline all are the same, right? Here, volume of the gasoline are the same as volume that is partially merged or coming down of the surface of the fluid and also inside of the fluid. And this is going to be half of the container. So all are the same. That's denoted here. And what is the W of empty part? Keep it in one side, right? FB. What is FB? Is V of displaced or V of the object. Let's write that. V of the gasoline, right? This is V of the gasoline times the gamma of water. And bring the W of gas to the other side. So minus gamma, minus the V of the gasoline times the gamma of gasoline. And we can write that the W of E is equal to the gasoline times gamma of water minus gamma of G. Gamma of water is, I wrote it here for you. The gamma of the gasoline is 6.5 kilonewton per meter cube, and gamma of water is 9.8 kilonewton per meter cube. W of the empty space is the volume of the gasoline, which is 2.25 meter cube times 9.8 minus 6.5 is equal to 0.425. Any question? No question? Perfect. Okay, guys. We're almost done with chapter 2. I tried to solve a question for you in the buoyant force. And also I've uploaded in the additional, or not chapter 1, but it's additional topic plus example. One more example for manometer. Then you have access to. I will try to solve more questions, but we still have time during the office hours to maybe solve some bunch of the question for you guys. But right now, all the materials for homework 2 is covered. It's going to be uploaded and it's available tonight at midnight, exactly the time that is your deadline for homework 1. Tonight you will have access to homework 2. All the materials are covered. That's it. Thank you so much for coming. Any questions? If not, you can leave.
Thank you.
Welcome.